Thanks, Ken. So today I'm going to talk to you about why life is a comonad. So a little bit about me. Like Ken mentioned, I'm a lead developer at IBM, where I work on infrastructure stuff. If you're interested in any more detail, come talk to me. I'm an enthusiastic Scala developer who's passionate about functional programming, but I'm not a theorist, and I'm not an expert in category theory, even though I'm talking about some category theory concepts today. So I mentioned, I'm not an expert in category theory, but I have been learning a little bit about it and studying some of the ideas. And one thing that struck me is the idea of duality. So any category theory construction, you can build an opposite construction by reversing all the arrows. And so I use monads in my day-to-day work quite a lot in Scala, and I thought that a good starting point would be to learn about comonads. And sort of explore that idea. But one thing I found is a lot of the resources online are in Haskell, which I'm not an expert in, and I found them a little bit hard to follow. So I sort of went and learned Haskell so that I could learn comonads and translated that to Scala so that we can sort of have a resource for the Scala community as well. So a little bit of a game plan for what we're going to talk about today. First of all, we'll start with a definition of comonad and how it relates to monads. We'll look at a data structure called the zipper as a metaphor for comonads. And now that I think about it, I'm not sure even my definition of metaphor here is correct based on the keynote this morning. And then we'll implement Conway's game of life, leveraging some of the capabilities we get from our zipper data structure. And I guess the intention here is not to dive into the sort of theoretical sort of underpinnings of comonads and category theory, but to convey a sort of conceptual idea of what it is and an intuitive understanding of what a comonad is and how certain examples behave. So what is a comonad? So it's the dual of a monad, obviously. So here we have some Scala syntax, I should have mentioned. All the examples in this talk are going to be in Scala. So in Scala, you define a type class with a trait like this. And so at the top of the slide there, you can see we have the definition of a monad, which has two functions. It has a unit function, which wraps some pure value, and then has a join, which sort of merges two F structures in some way. So you can think of that of like option or maybe, or either. There's lots of examples. So if you kind of squint, you can see that we're reversing the arrows in our definition of comonad. So co-unit is the opposite of unit, and co-join is the opposite of join. So with co-join, we're sort of pulling a value out of our F structure. With co-join, we're sort of, in some sense, duplicating the F structure. And so we rewrite those signatures a little bit differently using the function syntax. We can see that the reversal is a little bit more apparent. So this sort of obligatory analogy. So unit from a monad takes an apple and puts it in a box. Co-unit from a comonad takes the apple out of a box. So join from monad in some sense throws out one of the boxes or merges them together in some way. And then co-join adds an additional box. I know this is where this sort of analogy kind of falls down a little bit because it doesn't really convey the details of what co-join does, which is really where the meat of the comonad is, but we'll dig into that more as we go along. So as I mentioned, in a monad unit takes a pure value and wraps it in some F structure, and a comonad, the co-unit function, pulls the value out. And join and co-join, so join merges your F structures together, and co-join duplicates your F structures. So just revisiting the definition, have a look at this, try and remember it, but we'll see some more as we go on. So that's the definition, but it doesn't really give you an intuitive idea of how comonads behave. So we're going to have a look at a data structure called a zipper. So a zipper data structure has one sort of distinguished element. You can think of it as a focus or a cursor element. And then two linked list data structures. So one on the left-hand side has all elements preceding the current focus in reverse order. So you'll notice that the arrows are pointing to the left, and the elements on the right follow the focus element, and it's in the regular order. And so by using this, we can sort of leverage the fact that it's O of one time to append to a list to then shift our focus element to the left and to the right. So this is an example of moving our focus to the left by one. So if we start off with the zipper at the top of the slide there and we want to move left, what we do is we take the head or the first element of our left list and make it the new focus. And then we take our previous focus element and prepend it to the list on the right. So we've used O of one operations in all of those 3 steps. And we've shifted the focus one element to the left. Here's another example of moving right. I won't go through the details. So this is the basic code we use in Scala to encode our stream zipper, or our zipper data structure. In Scala, a stream is a lazily evaluated collection. So it can be an infinite set of items. So we have our focus element, and we have our stream of elements on the left, and our stream of elements on the right. This is just for demonstration purposes. It's not a total function because I have that called a head in there, which is not total. But if you look on GitHub, which I'll link to later, I have a slightly different implementation that is total. But you'll see that each moving left and moving right, I simply go through those 3 steps that I mentioned in the diagrams. So you might be thinking, what's that got to do with comonads? And if you remember back to the definition, our co-unit function extracts a value from an f of a structure. So if we set our f, in this case, to the stream zipper, then implementing that function becomes trivial. We just need to access the focus element. So at this point, we have half of a comonad, because we defined our co-unit function from our comonad by simply accessing the focus element. But what about the other half? So we need to generate a stream zipper of A, so multiple layers of stream zipper. But the key insight required here to define that is that we want to duplicate the data structure for every element within it. And there should be a duplicate copy of the data structure with the focus set on every element within the data structure. So I've got some diagrams to help illustrate that. So if you imagine we start with the zipper in the center of this slide, and then we call cojoin on it. So we first create a duplicate for the element on the left-hand side of the focus to generate the zipper on the top. And we also retain the one we're cojoining, that's the one in the middle. And then we shift one to the right and we duplicate the structure, and that's the one on the bottom. Also, it's important to note that since we have 2 layers of stream zipper here, we also need a focus element for the outer layer. And that's what the dotted lines here are demonstrating. So this is how we implement this. So we start off with 2 helper functions. We have lefts and rights. And what it does is simply repeatedly applies our move left function until we reach the end of the data structure. And so at each step, we're shifting the focus one to the left and creating a duplicate of the data structure. And similarly for right, except we apply the move right function. And then to implement the cojoin based on that, we simply instantiate a new stream zipper with our lazily evaluated collection of left duplicates and our lazily evaluated collection of right elements, as well as the current one. So now that we have these 2 functions, defining the rest of our comonad instance becomes pretty straightforward. We already had the co-unit implementation available by accessing the focus element, and we complete our comonad by defining the cojoin by simply delegating to the cojoin function we just defined on the data structure. So what we've seen so far is that a comonad is the dual of a monad, and we obtain the definition by simply reversing the arrows in the definition of monad. That has 2 operations, co-unit and cojoin. And a list zipper is an example of a comonad that sort of conveys some intuitive understanding of how most comonads operate. You might be thinking that monads have a pretty useful operation that you use a lot called flat map or bind. So what's the equivalent of that in a comonad? What's the opposite of that? And how do we define co-flat map? Well, we actually derive it. So you might have noticed that I used a slightly different encoding of monad than what you would be used to. Generally, a monad is defined with two primitive operations being unit and flat map. But in this case, I've used join instead, which is slightly different but equivalent. And so we can derive flat map from join, but we do require a functor instance. So similarly for the comonad, we can derive co-flat map from co-join, but we also require a functor instance. Something important to notice on this slide is the signature of the function that's passed to co-flat map. So it actually takes an f of a and returns a b. So it's taking one of those copies that we generated when we did a co-join, one of those copies of the data structure, and reducing it in some sense. Whereas flat map is taking a pure value and generating a new structure. So you can think of a monad in some sense to be a producer, and a comonad in some sense to be a consumer. So this is how we implement or how we derive flat map and co-flat map based on those definitions. So in flat map, we first map over the data structure with our function, and then we'll have two layers of f. So we use join to collapse it down. In comonad, we do the reverse. We first co-join to duplicate the structure, and then apply our reducing function that's past the co-flat map. So I have some pictures here to help. Not yet. So let's build up a mental model of how co-flat map works. The function past the co-flat map can be thought about as a local computation. So since it's receiving a copy of our data structure with the focus set on some individual element, it can compute a new value relative to that current focus. So it can move it can use some of our movement operators to move left or move right, move up, move down, and compute some new value based on that. So in our derivation, we first use co-join to get a view of the data structure from all possible perspectives. So you can kind of think of it as being, you're sitting on each element within the data structure and looking around you and trying to figure out what the new value of where you're sitting should be. So then we used map to apply our local computation to all of those different perspectives. So this is some images to help sort of understand how that works. So we've kind of seen this diagram before. This was the same one we looked at before, where we co-joined a zipper, we duplicated it out based on every element within the data structure, and then our derivation applied map to that. So then by applying our local computation at each one of the duplicates, we can do some computation relative to the focus and replace that value with the new value we've calculated. So co-flat map extends a local computation into a global context. So this is one of those very terse sort of phrases you might hear online when you're researching comonads. And I hope that I've sort of given you an intuitive understanding of what it means now and how you can sort of use these analogies to help understand what it means. Okay, so now a short example of, a simple example of how you can leverage the power of co-flat map. So in this example, what we do is we take the current focus element from the zipper, the focus one element to the left, and the focus one element to the right, and compute the average. So you can think of this as the local computation, and it has the same signature as the function applied to our co-flat map. Passed to our co-flat map. So what we can do here is we can construct a new stream zipper of 1 through 7, and then co-flat map our average function that's relative to the current focus of that stream zipper, which will then give us a sliding average of those three elements within our zipper. So we're looking at like 1, 2, 3, 2, 3, 4, 4, 5, 6, and compute the average of each of those groupings. And you can imagine extending this to arbitrary ranges that's not just 3. Okay, so now let's move on to implementing Conway's game of life using our Comonad data structure. But let's just start off by what is Conway's game of life. So it's a two-dimensional grid of cells where each cell is either alive or dead. And at each evolution, the state of the cell is controlled by the liveness of its neighbors. So these are the rules. I won't go into too much detail, we'll look at the code instead. So modeling our solution. So the next state, like I said, the next state of an individual cell is controlled by the liveness of its neighbors. So it's sort of controlled or determined by its local neighborhood. And the rules, each of the rules need to be applied at every cell, and then extended from a local definition at that cell to apply to all cells. So that should be reminding you of what CoFlatMap does. It extends the local computation to a global context. So we'll use this sort of alignment of CoFlatMap and the definition of the finite state automata for the game of life to implement the game of life. So the first thing that we need to do is that since our stream zipper is a one-dimensional data structure, we need to extend it into 2 dimensions in order to define a grid. So here we just have some simple helpers. Well, I guess to start with, we just nest the stream zippers. You can think of it as like a 2-dimensional array in some sense to create a 2-dimensional grid. So we have a stream zipper where the outer stream zipper represents 1 dimension and the inner represents the other dimension. So we just have some helpers here to move up and move down that delegate to the appropriate layer. The co-unit definition is simply just dereferencing two co-unit functions. And the co-join one is a little bit more involved. So in order to define co-join for our grid data structure, we basically need 4 layers of stream zipper. So we define a helper function called layer that takes 2 layers of stream zipper and adds an additional one. And if you study this implementation, you'll see that it's quite similar to our original definition of co-join on stream zipper itself, but it needs to leverage the fact that we're iterating over stream zippers and that they're a functor. So we basically apply this function layer twice to generate 4 layers of stream zipper, and then map over that with our grid to then get our 2 layers of grid. So now that we have that, we can move on to what CoFlatMap would look like. So we actually use the same derivation that we applied before, so we only need to define CoJoin, and we sort of get CoFlatMap for free because we've derived it in the type class. But here, this is what our effective signature for CoFlatMap will be. So we want to take a grid of A and return some B. So in our case, to implement Conway's game of life, what we want to do is to find that F function to apply the rules of Conway's game of life. So we're going to use a Boolean to represent the liveness state of each cell, so true being alive and false being dead. And we're going to look around to our neighbors based on the current focus element. We're going to find all of the neighbors and compute how many there are. And then we'll use CoFlatMap to extend our local definition of the rules to apply in all scopes. So our function is going to look like this, the Conway function there. It's going to take a grid of Booleans and return a new Boolean that will replace the current focus element. So what we do here is we first find the neighbors of the focus of our grid, and then we count how many there are. So that'll tell us how many live neighbors we have. Then we find the focus element of the current focus element of our grid, and match on that. So if the current the current element or current cell is alive, and the live count is less than 3, we die. If it's alive and it's equal to 2 or 3, it remains alive. If it's alive and the live count of its neighbours is greater than 3, it dies as if by overpopulation. And if it's dead and the live count is 3, then it sort of regenerates. Just for completeness, this is how I found the neighbours of the current focus element, just leveraging the move left and move right, move up and move down functions we defined. Alrighty. So using that definition and a few helpers to repeatedly apply it at each generation, I've got a console-based game of life here. It gets stuck there. So let's review what we've seen so far. So we've explored the definition of comonad. We've provided an intuition for comonads using the zipper data structure. We've demonstrated the use of comonad to solve a programming problem, both the sliding average and by implementing Conway's game of life. So I have a blog post on the same topic, if you'd like to look at that, and the full source code for this is available on GitHub. And there I have a couple of alternative implementations, one using the store comonad, and one using a generalized store comonad based on representable functors. So if you're interested in any of that, you can come and talk to me, or you can have a look at the code there. And also these slides are available online as well. So we're hiring, so come and talk to me, or go and have a look on LinkedIn if you're interested. And questions?
Does using the comonad approach to using the zipper force you down to a particular representation of the grid in the final example? Some people use left-right wraparounds, pretend it's on a toroid or other representations like that.
Yeah, I don't think you could do the wraparound with the zipper data structure.
What else?
But yeah, so my alternative implementation using the store comonad, you basically end up having a mapping from a pair to a value, and then you could, based on the the inputs to that pair, based on the indices, you could do wraparound if you wanted.
Yeah, g'day. My question, so that was, to me, a really good explanation of Comonads. And my question is about explaining Comonads, if that's all right.
Sure.
So you're down at the pub, and someone goes, what's a monad and what's an example? And you go, well, you know how when you have a list of lists and you collapse them down to a list, and then everyone says, yeah. And, you can get through that pretty quickly and easily, and most people will get through that. Do you have a similarly easy explanation for Comonads? Because I do not.
I do not either, and that's like one of the reasons that I wrote this blog post and why I went through such a detailed process of explaining what they are, because I don't think I haven't been able to come up with like a one-liner like that can really convey the idea of comonads, because it's quite a difficult thing to understand, I think.
All right, that's me too.
But one example that I've found that sort of help people understand is the idea of, especially people in tech, if they know how image compression works. You think of like JPEG compression, where you have you take a bunch of pixels and you can reduce it into one pixel. So people who understand that can help them to understand. But yeah, and the zipper one as well, I think, is a good one.
I was actually going to just say image things like blurs and so on are one of the things that was explained to me. But you used it anyway.
Do I have a bit of time left? Anyone else?
So with the what was it, co-join for Comonad, can you explain why you have to go, like why each zipper in the zipper has to be stepped one along, like corresponding to its position? Like, why does it have to be that way? Why can't I just have the same one duplicated everywhere?
It could, but then it would violate the laws. Where's George? And I intentionally didn't talk about laws because I wanted to try and convey the intuition instead. I think I have a slide at the end with the laws defined. Yeah, there you go.
Anyone else? I have one last question. Oh.
Thank you, Eli.
Thank you.